Welcome back to section 5 of chapter 10 on parabolas. This is the last section that we're going to be looking at the types of conic sections. After this, we'll be working a little bit with them. So this is the last one with all sorts of vocab and stuff like that. Parabolas, you might think we're really good at parabolas. We spent a whole chapter on parabolas. Chapter 5. Not quite. Chapter 5 wasn't on parabolas. It was on quadratic functions, whose graphs are parabolas. But parabolas are more than just quadratic functions. As we can see with this parabola, that's not a function at all. But even so, it still is very closely related to quadratic functions. So some of what we'll see will be a little bit the same, but some of it will be a bit different. So let's look at some of our learning targets. I can write the standard equation of a parabola and its axis of symmetry. And I can graph a parabola and identify its focus, directrix, and axis of symmetry. So before we really get into parabolas, let's look at what is it. The definition. A parabola is all points that are equidistant from a fixed point, the focus, and a line, the directrix. That's a fun word to say. You should try it. Directrix. Go ahead. No, actually, go ahead, say it. No, out loud. Gesundheit. Alright, so, what does this mean in a graph? If we have our parabola and we pick any point on this parabola, say that point right up there, the distance from this point to the focus, and the distance from this point to that line, and when it hits the line, it's the perpendicular distance because that is going to be the shortest distance to the line, where this guy right here is a right angle. Those two distances are the same. So m and n, m equals n. With ellipses, we found the two distances and we added them together. With hyperbolas, we found the two distances and we subtracted them. With these guys, we're going to find the two distances and set them equal to each other. So it's very similar to what we've been doing. So what are some uses of parabolas? And I put in paraboloids. A paraboloid is a parabola that's been rotated, so it's like a 3D thing. Some of them, we have a parabolic heater, and I actually have one of these in my classroom. I'll turn it on so we can see. But what happens is this is at the focus. I mean, this is cheap, so I have coiling rings or heating coils. If it was a really true one, it would have a point of heat, which would be very, very expensive and possibly nuclear. But it would have a point of heat. What happens is the heat radiates from here out to the different points of the parabolic dish, and from there it reflects and it all points straight out. So when I have this on, it puts heat out in the line. If you put your hand to the side of it, you don't feel anything. But anywhere in front of it, you feel the heat radiating. And so here, stuff starts there, and it goes out. Another use is a parabolic microphone. You've probably seen these on football fields. I tried to get one with less about the guy holding it, but this one I was actually able to see the microphone as well. I cannot remember what this guy's name is. It's a picture I found on the internet. My source is the internet. What happens here is the sound comes straight in from outside, wherever he's pointing it at. It hits the parabolic dish, and that all reflects back into the microphone, which is in the center, pointed back at the guy. The microphone isn't pointed out into the field. It's pointed at the dish because all the sound comes in and hits this, and then it bounces. Another use, which is very similar to the parabolic microphone, is a satellite dish. Now here I have a Dish TV, DirecTV type dish, but even the old school satellite dishes, the really big ones, function the same. What happens is the signal comes in from space in this case, it hits, and it all bounces back to the receiver, the microphone, which is pointed back at the dish. And then what's amazing about it is if we cut it off at a certain point, parallel to the dish itself, the line, or the length it takes to get there and then here, here and then here, that's all the same. And so it hits at all the same time, which allows us to get HD quality stuff from this little dish. Same thing. It allows us to pick up the sound. If it was all hitting at different times, the sound would be garbled. But all the sound waves hit at the perfect time because the distances are the same. That's not so important with the heat. You can't tell how long the heat has been out. Another use that we see a lot of is in flashlights. You look inside, this little reflective thing is a parabolic curve. The light shines out from here, hits it, and then goes straight out. That's why your flashlight has a beam of light instead of just kind of a bright flood that you'd see with your bulb. Same car headlights do it. The light actually shines backwards at the car. It reflects, and then that shines out. Most car headlights do it that way. And so parabolas and paraboloids have a ton of uses, and they're very exciting. So let's look at some of the equations and vocab. There's less vocab in parabolas, but we do have horizontal and vertical ones. The horizontal ones look kind of like the one that we just saw. The vertical ones look like the parabolas that we know and love from Chapter 5. Each of these parabolas has a focus. That would be the one point. There's only one focus in a parabola. It's just the one point. And notice it's inside the curve. The closer the focus gets to the vertex, which we haven't talked about vertex, but we know what the vertex is. The closer it gets, the skinnier the parabola gets. And the further away you pull the focus, the closer to a straight line it gets. But we have the focus. We have the directrix, which is this other line that's on the other side of the parabola. Notice the distance from the focus to the vertex is the same as the distance from the vertex to the directrix. Same thing here. We have 2 units in both of these cases. Then the vertex, which I've been using the word vertex like you know what it is, because you do. It's that point, the maximum, minimum. It's the turning point of the parabola. And then really the last thing we have is the distance. This distance, which is the same as this distance, the distance from the vertex to the focus, which is the same as the directrix to the vertex, which over in the vertical ones, same idea. It's a different distance than this one because it's a different parabola, but it's the same. And this distance, we call the distance p. Obviously, we're going to use p. It makes perfect sense. It doesn't. I have no idea where the p comes from. But maybe it's p for parabola. I don't know. Anyway, that's the distance p. And we're going to use that in our equation because our equation, the basic one, for horizontal, x equals 1 over 4p times y squared, where p is this distance. So if you know a vertex and a parabola, or a focus, you can find the equation of a parabola. If we wanted to move the vertex so it's on the point h comma k instead of 0, 0, we do the exact same thing we've been doing. X minus h, y minus k. Everything else, the 1 over 4p stays, and we get the general form of the equation for the parabola. Equations for other stuff, the focus. The focus is going to be at the vertex, and we're going to go p units horizontally to the right. So if the vertex is 0, 0 and we go p units to the right, we're now at the point p0. If the vertex is at h comma k and we go p units to the right, it's h plus p comma k. The directrix is a line, so it'll be x equals or y equals. A vertical line, in this case, is x equals p units this way. Well, if we start at 0, 0, it's just x equals negative p. If we start at the point h comma k, we subtract p to the x, it's h minus p, just x equals h minus p. And then the axis of symmetry is the y value here. So here the x value was, we used 0, 0, we've used the x value a couple times. Now it's just the y value, y equals 0. Or, in this case, y equals k. And so, we can get the different things. Notice it's just the y part of the axis of symmetry, or of the equation, the vertex. So that's for horizontal. Vertical is going to be the same. We're going to switch the x and the y. Notice here we have x equals y squared. Vertical, which is the type of parabola that we know and love from previous chapters, we had y equals x squared. That's going to give us vertical. So x equals is horizontal, y equals is vertical. And notice we still have 1 over p, x squared. And then if we move the center, or the vertex, it's just y minus k and x minus h. Same way we changed it over here. Same way we changed circles and ellipses and hyperbolas. The focus, now instead of moving in the x direction, we're going to move in the y direction. So if we start out 0, 0, we go up p, we're going to be at 0, comma p. If we start at h, comma k, and we go up p, we're going to be at h, comma k plus p. The directrix, we have to go down, so we'll be at negative p, or k minus p, and this is a horizontal line, so it's y equals negative p, y equals k minus p. So notice, if the equation is x equals, the directrix is x equals. If the equation is y equals, the directrix is y equals. And the axis of symmetry is going to be the other one. We had y equals when it was horizontal, and for vertical, we're going to have x equals the x part of the vertex, which would either be x equals 0 or x equals h. And so these are two of the ways our parabolas could look. They could also be negative. It could flip backwards and have it open to the left instead of opening to the right, or it could open down instead of opening upwards. And so what happens? Well, the p is just negative. If our focus was on this side of the vertex, the distance from the vertex to the focus, a directional distance, would have been negative. If we make p negative, all of these equations still work perfectly, because the x, or the directrix, x equals negative, negative something, would be a positive number. The directrix would be over here. Same thing with the focus. If p was negative, h plus a negative number would take us back to the left. So to find p, you always want to go from your vertex to your focus, or from your directrix to your vertex. That will find p. If you go the other way, you end up with negative p. So let's see what we're going to do with these. We can use the distance formula to find the equation of a parabola with a given focus and directrix. So if we have a focus 0, negative 5, and a directrix y equals 5, we can just use the definition with the distance formula and find the equation. We can do this with the ellipses and hyperbolas as well. Gets a little bit ugly sometimes though. For these, we're going to do the distance equals a distance. We're going to go with a point on the circle, and the point on the parabola, and the point on the parabola is just going to be xy to the focus. So we'll find the distance there, and the point xy to the directrix. And the point we're going to use for the directrix, well, we know y equals 5. What does x equal? Well, x is going to be the same thing as it is here, which is just x. So we're going to find the point we're going to use the point x comma 5. So the distance from xy to 0, 5, going to have the square root of x minus 0 squared plus y minus negative 5 squared. And then the distance from xy to x5 is going to equal square root x minus x squared plus y minus 5 squared. We can simplify this. So x minus 0, that's just x squared. Here the x minus x is just 0. One of these goes away. That'll happen every time you do the parabola, because that will, otherwise it would cancel out and we wouldn't have anything squared. And so we'll see what happens there. But when we do this in a parabola, either one of the x's or one of the y's will cancel out. So this is just 0. Minus negative is positive, so we could simplify it a bit. They're both square roots, we square both sides. We have x squared plus y plus 5 squared equals 0 plus y minus 5 squared. We can distribute the y plus 5 squared and y minus 5 squared. This is not y squared plus 25. We need to have that plus 10y in there, and this will have a minus 10y in there. So when we distribute, we get this, and then we can move things. Well, we have a y squared and a y squared, so those are going to end up canceling each other out. We have a 25 and a 25. Those are going to cancel each other out. So if we just subtract the 10y, we get x squared equals negative 20y. We want y equals something, so, or x equals something, but in this case, since the x is squared and the y isn't, we want y equals something. So divide by negative 20. So y equals negative 1/20 x squared. So this is going to be vertical because it's y equals. It's going to be upside down because that's negative, so it'll open down. And this is 1 over 4 times p. Well, 4 times what equals 20? That would be 5. So the focus would be 5 down from the vertex, which is 0, 0, which, hey, look at that, 0, negative 5. Notice this also figured out whether it was horizontal or vertical for us because of what canceled there. So that's one thing we're going to do. It's pretty similar to what we were doing with ellipses and hyperbolas, where we were either adding or subtracting the distances, but we're setting them equal and solving them, and we still have variables in them, so we end up with an equation instead of just a number. Another thing we're going to be doing is writing an equation in standard form. If we have a graph here, so here we have a directrix, we don't know where the focus is, but it's going to be the same distance away as the directrix. But things to notice, this is opening it's opening horizontally, which means we'll have x equals 1 over 4p y squared. And then we want to figure out what p equals. We don't have a focus, so we can't go from the vertex to focus, but we can go from the directrix to the vertex. What's this distance? Well, the directrix is at negative 2, so p equals 2. Because to get from negative 2 to 0, we're going plus 2. Just plug this in for p. X equals 1 over 4 times 2y squared. Multiply. X equals 1/8 y squared. There's the equation in standard form. We can write the equation in standard form if we're given some information, like a vertex and a focus. So, things to see, is this horizontal or vertical? Well, what's changing from the vertex to the focus? The x value is changing. That would make it horizontal. So, and the vertex is again 0, 0. So we have, and p, to get from the vertex to the focus, we go negative 8. So p equals negative 8. It's horizontal, so x equals 1 over 4p times y squared. Just plug in negative 8, and we get x equals negative 1/32 y squared. Notice we plugged in the negative 8. It took care of that negative. It took care of flipping it for us. And then find a whole bunch of stuff, and then graph it. So, if we have an equation, y plus 1 equals 1/16 times x minus 2 squared, we can find the vertex. The vertex, same as finding the center of any of the things we've been looking at. We have y minus negative 1, so the y part is negative 1. The x part is 2. Big mistake here is just go negative 1, 2. I'm putting them in the order you get them. Pay attention to what's x, what's y. X has the 2, so the vertex is 2, negative 1. The value of p, well, 1/16 equals 1 over 4p, which means 16 equals 4p, which means p equals 4. And you might need to do that showing work, depending on what the value is, but most of the time, you're going to be able to figure out what p is pretty easily. Axis of symmetry. Well, this is y equals, so the axis of symmetry is backwards. It's going to be x equals the x part of the vertex, x equals 2. The focus, if we start out at 2, -1, and our p-value is 4 in the y direction, what is -1 plus 4? 3. So the focus, 2, 3. The directrix, we just go backwards. So we went -1 plus 4. Let's go -1 minus 4. Gives us -5. The directrix is y equals -5. And then graph it. To graph it, start out with our graph paper, plot the vertex, which was 2, -1. I would plot the focus, plot the directrix, and then sketch your graph. You can plug in some points if you wanted to. If x equals -1, x equals 0, you can use symmetry to help you out with that. But then just sketch your graph, and you're good to go. So we've seen parabolas before. They are the same, but we didn't have p. We had to do a lot of other stuff. Now these are actually, I think, more simplified because we're just looking at the parabolas, not the quadratic functions, and so there's less to do. But this is what we're doing. A lot of the stuff is going to be the same type of question that we've been doing for the rest of the conic sections, and that's basically it. Again, this is the last topic or the last type of conic section we'll be looking at. After spring break, we will be looking at solving systems and telling which one's which and things like that. And it's a bit easier, but this is what we'll be doing tomorrow. So I will see you then, and have a good evening.